psi1 squared is equal to 0 and psi2 squared is equal to 0. I don't have time to go into this, but this, because for this moment, this by themselves is a very wide field to study such quantum planes and Grassmannian quantum planes. At this moment, I only want to, what only we want is to say the following. If we suppose that the quantum plane and the Grassmannian quantum plane can be will be preserved by matrices, then we will obtain for the matrices these relations. Actually, we have written how things are transformed by matrices. This we did already on the first lecture, and maybe even for the lecture of freshmen. That the two coordinates x1 and x prime, they are transformed by some matrix. Let me call it A, B, C, D. Same matrix M, x1 and x2, which of course means that the new coordinates will be replaced by the old coordinates is x1 plus bx2 and cx1 plus dx2. And I want the same thing from the same relations. Now, what I want is the following. I have now these relations. So x1 prime is a linear combination. Linear is not a good word to say, but it's a combination of x1 and x2 with coefficient, the operators A, B, C, and D. And now, and what I want now is that x1 prime, x2 prime, I require this is requirement, will be q x2 prime, x1 prime. So the primes will have the same relations as these ones. And the same thing I require maybe I will delete this because this is already another part of the lecture. I require psi1 prime, psi2 prime is minus q minus 1, psi2 prime, psi1 prime, and psi1 prime squared is equal to psi2 prime squared is equal to 0. So now I give you another exercise. So now we have a simple exercise. You substitute x1 prime with this. You substitute x2 prime with this. Then you have the same qualities with psi1, psi2. And you substitute them into these equations. And you have to recover that they hold. And in the process of proving that they hold, you will show that for A and B follow these relations. So from the requirement that the matrix A, B will serve as a transformation matrix of the quantum plane, and the Grassmannian quantum plane will recover these relations. So these relations are not accidental. Now, what more I wanted to say? Now, what more I wanted to say? Okay, now I want to be able to, of course, what about I had to, of course, to introduce the coproducts and the antipode. So the coproduct now this is now a definition of delta of m. Delta of m will be given by the tensor product of the two matrices. So this means the following. Now let me write this as A, B, C, D, tensor A, B, C, D. This means that now this guy has to be something in tensor times tensor. And it can be written in a matrix way, in a short matrix way, in the following way. In the following way, just multiplying as I'm multiplying matrices. So I multiply this times this, so I have A tensor A plus B tensor C. I'll put here lines to separate. Then I multiply this row by this column, so it is A tensor B plus B tensor D. Then I have C tensor A plus D tensor C. Finally, I have C tensor B plus D tensor D. So indeed, so it means that, so of course, to put it in another way, let me separate these formulas to be sure they don't get mixed up. So in fact it means that here in this thing I have delta of the element A, here I have delta of the element B, delta of the element C, and delta of the element D. Now you have another exercise to show that the delta is an algebra homomorphism. It means that delta of A, delta of B must be equal to Q delta of B delta of A. So this is for, I have taken for instance this thing. It means that if I apply the delta continuously with everybody, then you have to follow this. And this is an exercise. You can just check it because you know what is delta of A. It is here. You know what is delta of B. You substitute the other order, and you must obtain this equality. And the same for all the other equalities. The same for all the other equalities. You can also obtain the delta of the Q determinant M is equal to the tensor product of the two Q determinants. So delta of Q is this thing. You know how to apply delta on this. You apply delta on A, delta on D, then minus Q delta of B, delta of C. And then on the other hand, you have to reorganize the two things so that on the left will be the determinant times on the right this determinant. This you have to do. Now, what is the antipode? What is the antipode? In this case, we have to use the inverse of the matrix M. Now, of course, it is how to say it is the inverse which we will write as if it is numbers, although it doesn't have the same meaning, but that's how it is. Let me